Okay, great. Thank you. Yeah, so this is joint work with Guilherme and Toledo, who's right there, and Yoni Zohar. So yeah, excited to share this with you all. So, okay, so a lot of my work has already been cut out for me because people been talking about theory combination for the last few talks, but I'll just recap it once again. So satisfiability modular theories, this is the problem of determining whether a formula is satisfiable with respect to some logical theory. And in this talk, I'm only going to be considering quantifier-free formulas, as is typical in SMT. And so there's a lot of decidable theories that are used throughout SMT, but in practice, we often want to reason about multiple theories at the same time. So this is what we typically want to do in applications like program verification. And I'll give an example of that in a minute. And so the central question of theory combination that we seek to answer is, if we have decision procedures for two theories, when can we combine them into a decision procedure for the combined theory? And the combined theory is just the theory where we take the union of their two axioms and we work over the union of their signatures. So we're allowed to use vocabulary from both theories at once. And in this talk, I'm only going to consider disjoint combination, which is where we're only working with theories with disjoint signatures, so they don't share any vocabulary. Okay, so just as an example, suppose that we want to check the satisfiability of a sentence like this. So you can see that we have f is some uninterpreted function symbol. I'm using the bold u to be an array that we're indexing into, and then I is an integer. So we have the less than or equal to constraint. We have plus, we have uninterpreted functions, arrays. So we're really working with three different theories at the same time here, namely arrays, linear arithmetic, and uninterpreted functions. And these are three theories that are on their own, each decidable. But the question is, how can we take those decision procedures and modularly combine them to decide the satisfiability of a sentence like this one? Okay, so that's the basic. That's the kind of the motivating. That's a motivating example for theory combination. Okay, so one example that I'm sure many people have seen is the Nelson-Oppen method for theory combination. So this was all the way back in the 70s. So what they showed is that theory combination is possible when T1 and T2 satisfy a property called stable infiniteness. And by possible, I mean the combination is decidable. So stable infiniteness means that for every T satisfiable quantifier-free formula, there's some infinite interpretation that satisfies this. In other words, you can think of this as saying that without loss of generality, we're allowed to work over only infinite models, because that's an essential assumption that's used in the result. And what they showed is that if we have decidable theories or disjoint signatures that are both stably infinite, then their combination is decidable. And it's important here that we're imposing a requirement on both theories. Okay, so that's just some background. I mentioned stable infiniteness. There's actually a bunch of these properties that show up. So we just heard about politeness. There's also shininess, and these depend on technical conditions like finite witnessability and the finite model property and so on. And a few years ago, the logical relations between all these notions were relatively poorly understood. So there were a few isolated results saying that some properties imply others, but the overall landscape wasn't well understood. And to rectify this, a few years ago, Toledo, Zohar, and Barrett began a systematic effort to classify all of the logical relations between these theory combination properties, by which I mean for any Boolean combination of those properties, the question is there a theory that satisfies all and only those properties? And I'm not expecting you to read or understand what this table is saying, but the idea is that they're taking several of these properties and they created a giant table saying for each Boolean combination, either giving an example of a theory satisfying the property or giving some negative result saying that such a Boolean combination is impossible. And this has yielded several theoretically interesting results and a better understanding of the properties. And it's also useful to people doing theory combination because sometimes it's easier to prove some properties rather than others. So you can sometimes prove some properties and then consult this table and say, okay, this tells me that automatically I know it has to satisfy another property that's useful in theory combination. Okay, so this paper is really a continuation of this line of work. And so it's quite fruitfully seen as the fifth in a series of papers about classifying Boolean combinations of combination properties that began a few years ago. Although our paper is self-contained, so you don't need to read these four first. Okay, so what are the contributions of this paper? So one thing we do is we complete the classification of which Boolean combinations of 8 properties relative to relevant to theory combination are possible. So that table I showed you, it's actually an even larger table now. We filled in every grid with either an example of a theory or a negative result. And in doing so, we have a few independently interesting results. So one is a new decidability result for so-called shiny theories, which I'll introduce in a minute. We also refine a result due to Casal and Hasga regarding the equivalence of shiny and strongly polite theories. So these are shiny, so you know what strong politeness is now, but shininess turns out to be equivalent to that modulo some assumption, and we examine what happens when you drop that assumption. Then we study conditions under which strong politeness is equivalent to additive politeness. So conveniently, we all just learned what additive politeness is, and we coincidentally were also investigating the relation between these two notions. And finally, we resolve an open problem about the relation between what they call finite smoothness and smoothness. Okay, so I'm going to touch on all of these bullet points except for the last one, because the last one is requires introducing some quite technical notions from model theory. So you can consult the paper if you're curious there, but I'm going to touch on the rest of these. Okay, so I want to talk about shininess first. So Tonelli and Zarba back in 2003, they proved the combination theorem that, unlike the Nelson-Oppen method, only imposes a requirement on one of the component theories. So namely, if we have decidable theories over disjoint signatures and T1 is shiny, then the combination of T1 and T2 is decidable. And importantly, we impose no requirements on T2 other than that it be decidable. So it's much easier to work with. It can be easier to work with than the Nelson-Oppen method, particularly when your theories aren't stably infinite. Okay, so let me define shininess. I should say that in the talk, I'm only going to work over single sorted logic just for notational simplicity, although all the results in our paper are stated over many sorted logic, which is typically used in SMT. Okay, so to define shininess, it's helpful to have this notion called the spectrum of a formula, which coincidentally was also talked about earlier. So the spectrum is the set of cardinalities of models satisfying that formula. And we denote that spec of phi. I actually want to restrict it to only be the countable cardinalities. And then we'll say that a theory is shiny if the spectrum of any formula is of this form. So it's an interval of all the cardinalities from n to aleph naught. And we require that n is finite, so it can't just be the singleton aleph naught. And also that n can actually effectively be computed given phi. So what we're saying is that each spectrum is nice in a sense. Now, often when you read the literature on shininess, you'll see this stated a little differently as the conjunction of the following 3 conditions. But this is equivalent. So one thing you'll see is that we require that the theory be smooth, and this means that for any cardinality in the model n, any cardinality in the spectrum, every larger cardinality is also in the spectrum. So we can always, if we have a model satisfying a formula, we can always grow the model to any desired larger cardinality. We'll say that the theory has the finite model property if for every satisfiable formula, it's satisfied by some finite interpretation. In other words, the spectrum contains a finite natural number. And then finally, we have this condition of the computability of the minimal model function. So the minimal model function is the function that we denote mid-mod that gives you the smallest model, the size of the smallest model satisfying a formula phi. In other words, the minimum element of the spectrum. And we require the minimal model function to be equal to this value whenever phi is satisfiable. Importantly, we don't place any requirements on what min-mod returns when phi is unsatisfiable. So min-mod can return anything when for unsatisfiable formulas. So it's really just saying the minimum size of a model, supposing such a model were to exist. Okay, so I know this is kind of a mouthful of definitions, but equivalently, you can define shininess as being the conjunction of smoothness, the finite model property, and the computability of the minimal model function. Smoothness tells us that our spectrum is some interval like that. The finite model property is saying that n is finite in that expression, and the computability of the minimal model function is saying that we have a way to compute what n is. Okay, so hopefully that made sense. So then in a similar spirit to shininess, there's this related notion called strong politeness, introduced by Ranius, Fingason, and Zarba, with a slight correction by Jovanovic and Barrett to fix a bug in the proof. And so their theorem said that if we have two decidable theories over disjoint signatures, and one of them is strongly polite, then the combination is decidable. So it's again, we're only assuming a property of one theory. And I'm not going to formally define these notions, but because they're a little technical, but roughly a theory is finitely witnessable if given a satisfiable formula. We can compute an equivalent formula that's satisfied by a T interpretation, in which every element of the interpretation is denoted by some variable in wit phi. So we call that the witness function. Basically expands out our formula to make explicit all of the variables that we need in a model. And roughly a theory is strongly finitely witnessable if it satisfies a similar property where we additionally impose equality and disequality constraints on the variables in wit phi. And we require that it satisfies the same conditions subject to these equality constraints. And then we'll say that the theory is strongly polite if it's smooth and strongly finitely witnessable. And similarly, we'll just say it's polite if it's only finitely witnessable and smooth. Okay, so there's a surprising result. These notions are defined quite differently, but it turns out that they're actually equivalent for decidable theories. So for a decidable theory, it turns out that it's shiny if and only if it's strongly polite. And what's interesting about this is neither direction of the implication is obvious. So it really is a surprising equivalence. It also gives, in some cases, it can be easier to prove strong politeness by showing shininess, for example. So it can also be useful for that. But one thing we might want to know is, what about for undecidable theories? Do we really need the decidability assumption here? So we were interested in looking at this because it was helping us fill in some of this cells on that table I showed you earlier. And the results is as follows. So it turns out that actually every shiny theory is decidable, and therefore, by the Casal and Hosga equivalence, strongly polite. So this seems to have been unknown before. But on the other hand, we were able to construct a strongly polite theory that's undecidable, and in particular, then it's not shiny by the previous two results. Okay, so I'm going to briefly talk about both of these results. So, okay, so here's just a Venn diagram summarizing what I just said. So for decidable theories, we have shininess and strong politeness coincide. We also show that every shiny theory is in this decidable region. There's no undecidable shiny theories. On the other hand, there are strongly polite theories that are undecidable and therefore not shiny either. And all the white regions in this Venn diagram are feasible. So we have examples for all of them, including outside of the diagram. Okay, so this proof is basically simple enough that I can actually give it on one slide. But first, let me address, you might think that this is somehow trivial or follows from the fact that we have a computable minimal model function, but that's actually not so. It's a little more subtle than that. And here's an example of a Peano arithmetic is an example of a theory that has a computable minimal model function, but it's not decidable, because we can just take the function that always returns aleph naught. And this works because if phi is satisfiable, then the minimal model has size aleph naught. But if it's unsatisfiable, remember that when we specified the minimal model function, it's allowed to return anything for unsatisfiable inputs. So this is a theory that is, in some trivial sense, has a computable minimal model function, but it's not decidable. So we can't just deduce, we can't prove this theorem using merely the minimal model computability assumption. We have to use a bit more. And in fact, we showed that we basically have to use all the requirements of shininess. So, okay, but here's the proof. So it's actually not too hard. So we'll take a formula phi, and our goal is to decide whether phi is satisfiable. So let k be the minimal model function evaluated at phi. And by the finite model property, we know that k is a finite cardinality. And so given that, let's introduce k plus 1 fresh variables, meaning they don't occur in our formula phi. And we're going to construct this disjunction that says this disjunction of either phi or all of those fresh variables are distinct. So we're saying either phi is true, or we have at least k plus 1 elements. And I claim that phi is t-satisfiable if and only if the min-mod function evaluated at that formula returns k. And the reason, so we can go through both directions. So on one hand, if phi is T satisfiable, then we know that phi has a model of size K. So in particular, this disjunction also has a model of size K. So the min-mod function should return K. On the other hand, if phi is not satisfiable, then this formula is actually just equivalent to this other disjunct, asserting that there's at least K plus 1 elements. And by smoothness, there actually is a model with K plus 1 elements. So this is where we're implicitly relying on the smoothness assumption. And so in that case, the minimal model function, if we have K plus 1 variables that we're asserting are all distinct, then the minimal model function has to return K plus 1, not K. So that shows the if and only if. So that actually gives a decision procedure for shining theories. So it's actually quite simple, but to us at least, it was a surprising result. Okay, so what about the other direction? What about a strongly polite theory that's undecidable? So I can give a brief outline of the construction. So what we do is we fix an undecidable set of natural numbers, and for technical reasons, I want all of the numbers to be at least 3. So this could be like indices of Turing machines that halt, for example, something like that. And we're going to work over a signature with only a single unary function symbol f. This construction actually would be a little easier if we allowed ourselves to use an infinite signature, but we like to show things over the smallest possible signature just to show that we're not actually relying on infinite signatures in any essential way. Okay, so I want to introduce this abbreviation, so I'll say cycle n of x, which intuitively means that the orbit of x under f is of size n. So more precisely, it means that if we apply f to x n times, we get back to x, and applying f any fewer than n times does not result in x. So I use this superscript notation to mean f of f of f of f of n, where it's n f's, or of x, where it's n. So it's f iterated n times. Okay, so just as an example, if we have a model like this, where, for example, f of c naught is c1 and f of c1 is c naught, c2, and so on, then cycle 6 of c naught holds in this model. And in fact, cycle 6 of c1 also holds, for example. So it's just saying that it belongs to a cycle of length 6. Okay, so then we consider this theory that has these axioms. So what it says is that if there's so we have this axiom for every n in S. So the way to read this is that if there's an element that belongs to a cycle whose length is in S, or undecidable set, then for every element, f squared of x is not equal to x. In other words, if there is a cycle whose length is in S, then there are no cycles whose lengths are 1 or 2. Because this rules out cycles of length 1 and 2. Okay, so this theory turns out is strongly polite. I'm not going to prove that here, both because I haven't formally precisely defined strong politeness, and because these proofs are a little technical. But that's in the paper. But it's actually not too hard to see that T is undecidable. So, for example, if you consider this formula here, cycle n of x and f squared of y is equal to y, I claim that this formula is T satisfiable if and only if n is not in S. And the way to see that is that if n is not in S, then we construct a model by taking a cycle of length n and containing x, and a cycle of length 2 containing y. And that's a model of the formula. And it satisfies the axioms vacuously. On the other hand, if n is in S, then having a cycle of length n forbids this condition. That's exactly what the axiom above says. It says that there's no cycles of length 1 or 2 under that constraint. So this formula, if n is in S, then this formula is unsatisfiable. So if we could decide the satisfiability of formulas in this theory, this would give us a way to query whether an element n is a member of S. But by our assumption, that's undecidable. S is an undecidable set. Okay, so that's the construction of a strongly polite theory that's undecidable. Okay, so at this point, I guess I've talked about shininess and strong politeness. So I should address the unicorn in the room and explain why we have unicorns in the title. So in prior work, this is not the whole table, this is just a zoomed in snippet. There were certain Boolean combinations of properties that they weren't able to determine whether or not they're feasible. That is, whether there are theories that satisfy those properties. And they call those theories unicorn theories. And there were various flavors like unicorns 1.0, 2.0, and 3.0. And as a consequence of the previous two results, we're actually able to answer all such questions. So for example, the theory that I just gave turns out to be a unicorn 2.0 theory. You can look at the paper if you want to know the exact definition, but it's basically exactly what we needed to fill in this table. So this is just a cute way of saying that for every grid on this table, we now have an answer as to whether we now either have a red box, meaning a negative result, saying it doesn't exist, or we have something like this, giving an example of a theory satisfying some Boolean combination of properties. Okay, so just to recap, so the shininess, strong politeness, Casal and Haska show that these are equivalent modulo decidability. We show that without decidability, shininess implies strong politeness, although the converse does not hold. Okay, so let me briefly mention additive politeness. So as we just saw, additive politeness is a useful tool for deducing strong politeness from weak politeness, because strong politeness is what we really care about in practice if we want to do theory combination, but weak politeness is often easier to show. And additivity, this idempotence condition, is a useful way to show that. So yeah, so additive politeness implies strong politeness, but what about the converse? The motivation for this is we want to know, is using additivity as an assumption, is this a complete method for showing strong politeness, in other words? And it turns out that unfortunately it's not. So we do have examples of strongly polite theories that are not additively polite. However, we have something close. So let's say the signature is algebraic if it only contains, if it doesn't contain any predicate symbols. So it's only function symbols. For over algebraic signatures, we are able to show that these notions coincide. So strong politeness is equivalent to additive politeness for algebraic signatures. So we can again summarize, add another blob to our diagram. So we have additive politeness was known to imply strong politeness, and we show the converse, assuming algebraic signatures, although the converse doesn't hold in general. So that clears up the relation between these notions. Okay, so now I'll conclude by saying that, so we refined the Casal and Haska equivalence between shiny and strong polite theories by showing that one implication, namely from shininess to strong politeness, holds without assuming decidability, namely because shininess implies decidability, although the converse does not hold. In doing so, we resolved all the remaining open problems from our previous papers regarding so-called unicorn theories. And what that means is that we've completed the classification of the Boolean combinations of a list of 8 properties relevant to theory combination, showing whether each subset is feasible. And as a nice side effect of this, so several of the theories that we've constructed for this project, we've had to construct a lot of theories that satisfy some conditions but not others, and this has resulted in having a nice stock of you might think of them as pathological theories that satisfy some nice properties we've cooked up. And that's been useful for a separate research program that we've been working on about impossibility results in theory combination. So earlier this year at CADE, we presented a paper about called Politeness is Not Enough, showing that weak politeness is actually not sufficient for theory combination, which justifies the introduction of strong politeness. And in doing so, we actually had to use some of the theories that we've introduced in this project. And so I expect this to have I expect this to be useful going forward as well. Okay, great. That's all I got. So happy to take questions.